I found a love for me. Just dive right in. Follow my lead. I found a girl.
Oh wait, can you show the name of the room you're doing?
I never knew you were someone.
Just wait for a few slides.
We were just kids when we fell in love. Not knowing what it was. I wanna give you up this time. Darling, just kiss me slow. Your heart is all I own. And in your eyes, you're all mine. I dancing in the dark. You could see my heart. Singing to our favorite song. When you said you loved me, I was. Found love for me. Darling, just dive right in. Follow my lead. Beautiful and so I never knew you were someone waiting for me. 'Cause we were just kids when we fell in love, not knowing what it was. I give you up this time. Kiss me slow. Your heart is all I know. Your eyes, you're all mine. Baby, I dancing in the dark. You see my heart. Singing to our favorite song. You said you loved me. I whispered underneath my breath. Nothing to
As I walked back to Grand Market. Yeah, All right. How many of you noticed that we played a song before the lecture?
Okay, how many of you know what's the name of the song? What's the name of it? Just what's it? What's that? This should be like one of the most popular songs in 2017, I believe. Like every time that I go to like H&M or some kind of like shopping mall, I always heard it. What's the name of it? What? Perfect, right? So today we are going to have a lecture that is also related to perfect because we are going to talk about performance. All right, so before we start, it's always a good idea to remind ourselves where we are coming from. So the last lecture, we spent a lot of time talking about the introduction about computer architecture. A lot of you might think, well, it's just the introduction, but it in fact gives you a lot of information regarding where we are in the world of computer architecture. And one of the most important messages that I need to let you know is that we are now living in a new golden age of computer architecture. And the reason why we lead to that is because we are facing problems in this conventional architecture called volume architecture. So so in fact, every computer, almost every computer you are using now, following the basic prototype of volume architecture in a way that your computer must have processors, memory, or some kind of storage device. And whenever you want to perform a function or say I want to use a program in this computer, it's always the case that you have a copy of the program that's already existing in the storage, or sometimes if you have an interpreted language, even so, you still have a script that has been in the storage. So it always starts with something in the storage, and then when we want to execute the program, either the compiled program can be directly loaded into the memory, or your interpreter or your virtual machine will translate the stored version of your program into somewhere in put it in somewhere in the memory that it will be the assembly instruction or the machine instruction that your processor can read. So because your processor can understand those instructions, so it's natural that your processor can fetch this compiled, interpreted instruction and execute those instructions line by line according to the program counter order. And if there is a case that you interface with some instruction that needs to access the data memory, that's a time when your processor will unload data from the memory or store data into the memory on demand. So the beauty of this kind of architecture is that by putting different programs into the computer, your computer can perform differently. So in this way, you don't have to physically reconfigure your computer, but you are still allowing your computer to perform different functions. And a lot of you might not think how this would happen, might never know how this would happen. So no matter what kind of programming language you are using, it all follows the same path in a way that, first of all, we have a source code, and you have some kind of programming language framework that helps you to translate those human-readable programming languages into the machine code, but in different processes. So for example, if you have a C program, turns out that you need a compiler, and the compiler would directly translate your code to the machine code that the processor can understand. And then whenever you need to execute a program, you just load the whole program into the memory and directly execute it. And if you don't change your source code, there is no demand for recompiling. And if you have a Java program, you still have a compiler, but instead of generating the machine code that your computer, your processor can directly understand, it generates some kind of intermediate assembly instruction code, or say machine instruction code, Java bytecode. It's in fact the machine code that the Java virtual machine can understand. So instead of directly put your program into the bare machine for execution, you need a Java virtual machine in the middle, and the Java virtual machine would fetch those Java bytecode instructions and interpret them into the native machine code on the processor that is running. So executing the program. So that's the process of Java. And a lot of you saying that, who's using C and Java these days? I'm using Python, right? So what about Python? So for Python, it's also similar in a way that you have an interpreter that whenever you execute a program, it runs in the backend to translate or interpret each line of your code into several machine instructions and help you dynamically load those instructions into the memory, and then your processor can execute those instructions line by line. But what's different from the C programming language is that for C programming language, whenever you get a program compiled, as long as you don't change the source code, you don't have to recompile it. However, for Python, you have to do it again and again whenever you are executing. So that's the big picture of computer architecture. That's the world that we are living right now. And today we are going to starting the first real important topic in computer architecture, and that's actually the most important reason why we are here learning computer architecture, even though a lot of us are not directly inventing new processors or change the memory architecture. The reason is because we want our program to act perfectly on this hardware. So, but how do we know if our program already act perfectly, or is there still room to improve? We have to know what's the performance right now. So today we are going to first talk about the definition of performance, and then we are going to talk about what are the factors that affect performance. So first of all, definition of performance. I believe most of you have finished the reading quizzes, so you should have some idea about what performance is about. So that's when we are going to start our first experience in peer instruction. So again, for peer instruction before the lecture, you need to complete the required reading, which I believe you guys did. During the lecture, we are going to have pop-up quiz, and first of all, you are going to individual thinking, and then we have a group discussion, and then a whole classroom discussion. So it's a process of a read, think, and discuss. So now make sure you have login call everywhere through the app or the website with your UCRNet ID. So yesterday I tried to use the Google, like they say, well, sign in with Google, but it turns out it also redirects me to UCRNet ID. So why don't we just start with the UCRNet ID? All right, and now after you log in, you have at least 90 seconds to answer the question. And the first question, I will give you more time on that, so don't worry about the timer. Try your best to finish your login. And now, you know what? One thing I forgot on my side. I have to log in first. You know, sometimes, oh shoot. What's that? Okay. Sometimes life is tough in a way that everyone has some kind of procedure, and what's the for everywhere? Here we go. Hopefully it's not asking me for, okay, and I hope I don't need to, but it's better to relaunch my Keynote again. Whew. Okay, so hopefully that will work out. All right, so now you have 90 seconds, and the website to log in is on the right top. Oh, yeah, sure.
Okay, this is the individual thinking, so be quiet. Yes?
All right. I guess most of you have voted, so I will count out for just 15 seconds. If you haven't made a choice, made a choice. All right. 5, 4, 3, 2, 1. Time is up. Okay. Yeah. Question.
I can give it to the board.
What? Did you? You are here already, and the reason why is because it's finished.
Yeah, I was trying to.
Before the contact, she's trying to end.
But did you log in first? I would say like log in and log out and log in again. Yeah. All right. So well, so sometimes like pre-pandemic and after pandemic, you start to forget that something that I shouldn't show this chart in the very beginning, so it's kind of misleading, right? So, but this is a question that just orients you through what peer instruction is. So now, even though we have a huge consensus on the answer, right? The second step of that is that please discuss with surroundings and make sure again that you vote after the discussion. All right, so go ahead. Discuss. I want to hear the noise.
And in the meantime, I will fix.
So, second. So like yeah.
Oh, really?
That's how I yeah, that one was tricky, but that's how
All right, let's wrap up in 90 seconds. Don't forget to vote. Yeah, you have to vote again. So that I know you guys are finished.
Yeah.
All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now, after the discussion, this is what we learned. Well, we learned that 43 of you think it's but anyway, well, so it's interesting. Sometimes it shows, sometimes it doesn't show. So, well, but they have the school content. All right. So can some of you explain how did you get the answer after the discussion? All right. What's your name? Would you mind to share with us?
Yeah, odds.
Okay.
So we know how many instructions there are,
Mm-hmm.
but we need to know how many cycles are running so that we can divide by the clock speed.
Mm-hmm.
And to calculate the number of cycles, we have to take a weighted average as the question provides, and then we divide the number of instructions.
Okay. So how do you? Okay. So now, assuming that you are the teacher, you want to teach everyone. So what's the first step?
Calculate the clock cycles.
Clock cycles. Okay. So how do I get the clock cycles?
You take the weighted average
I take the weighted average of what?
of the types of instructions. Oh, you want me to answer everything or?
Yeah, everything.
Oh, okay. Alright, so you take the weighted average of the types of instructions.
Okay, so how to calculate the weighted average?
You calculate the percentage of the type of instructions by the number of cycles that it takes.
So yeah, so can you like
I don't think you're right, Professor.
No, I'm not writing. Yeah, because I'm still waiting for him to tell me what to write.
I'm confused on I'm not describing it well, I guess.
Oh, well, okay. So tell me, what should I write now? Okay, tell me exactly. No, let him finish.
Don't say to me.
Sorry. You can do it. Thank you.
Oh, I forgot what I was thinking.
So it's difficult to participate in a game show.
Yeah.
Okay. Well, cool down. Deep breaths. Okay. Start from 0 again, right? What's the first thing you want me to write?
5 million instructions.
Okay, 5 million instructions is 10 to the 9, right? What?
Oh, yeah. Thank you.
Okay, 5 billion. Okay.
And then we have to write 3 gigahertz clock speed.
3 gigahertz clock speed.
Oh, wait, no. First we have to convert the cycles. Sorry.
Okay, convert the cycle. Okay.
I don't know.
Can you help me, Wyland?
Oh, yeah. 1/3 billion, you said? Okay, yeah. 1/3 billion.
Okay, 1/3 billion. Okay. What's the next?
Then multiplied by the percentage of the instructions.
Okay, so I have type A, 20%, right? And what it should be multiplied?
8,
8. Okay,
and then 20% by 4.
20% by 4. And what's in between?
Oh, in addition.
Okay, addition, that's subtraction, right? And what else?
And then we add the rest, which is 60% by 1.
60% by 1, right? And then you will figure out, well, this get canceled, and this part, I assume is something like 3, right? So that's how you get 5, right? Okay, so if you just put this in your homework or final exam, I'm not going to give you full credits. And the reason is because we want to make sure that you understand how you derive this answer. So here I'm going to show you what I'm expecting. So first of all, let's go back from how we get that formula first. Right? So the reason why you have that formula is because you read a book. There is something called performance equation. Right? So we define the performance as 1/execution time. And what's execution time? The execution time is how many instructions in a program. Because remember, as what we mentioned in a von Neumann architecture, the processors executes instruction line by line. Right? So how many instructions you have will directly affect how much time you would consume to execute a program. And then how many cycles that we need to execute an instruction. So if you have taken undergrad computer architecture, or at least you take the introduction to computers, you must know that most of the modern circuit we have something called cycles. Right? So presumably the processors are operating at the basis of cycles. So how many cycles that each instructions would take would also be a factor affecting how the execution time at the end. And finally, how much time it takes for a cycle. Right? So that's a performance equation, execution time, right? the number of seconds per cycle is actually 1 over frequency. So when you see like 3 gigahertz, you might be very excited that I want to put 3 at the end. But however, what you really want is 1 over 3 gigahertz because that's the cycle time. But 3 gigahertz is the frequency. And a very fast conversion that I have is that for 1 gigahertz is 10 to the 9 hertz, and it's basically like 1 nanoseconds per cycle. Right, so if you have 3 gigahertz, that's actually 1 over 3 nanoseconds. All right, and a very quick way to write it down is ET equal to IC times CPI times CD. So if you want to answer this question formally and make sure that you get as much credit, as many credits you want to get in any kind of answer, right? You have to write something like this first. Right? It's always like, okay, so how many of you have trying to be like ace in a coding interview? All right, so the thing is like, if you read a book, right, if you want to ace in a coding interview, it's always the case that you have to explain to the examiner, like, okay, why am I writing this code instead of writing this code first? Right? So you have to tell them that, well, for this problem, because of this. So we have to use dynamic programming. Right? So you always have to explain that first to get open. Right? Same thing here. This is like a training, right? I know you know the answer. I know you know how to get this equation. And in fact, I do understand what you are writing, but I also want you to practice that in the future when you answer a question that always try to define the question well, try to, tell people why am I using this solution to solve this question. So in this way, even though like there are some mathematical error at the end, I can tolerate because sometimes if you don't have that formation comes first, then I have no idea what you are doing. So that's why I think it's important that you have this practice every time in the future. All right. Okay, so with that performance equation, right, we get the execution time. And again, execution time is the simplest kind of performance, and the shorter execution time is better. Yes.
So you said that on the test, like that, the answer that we came up with before, we can get full credit because you want an explanation. How would you, like, what do you mean by explanation? Do we need to write a paragraph explaining why?
No, but at least give us like at least write down like, okay, because we are, well, just like a sentence is good. Yeah. Okay. All right. So for the execution time, right? So it's the simplest kind of performance. And again, why we come up with that equation is that if you think about how von Neumann architecture is execute program, right? It's a processor, and in your processor you have a register called program counter, and there's a clock controlling the cycles of the processor. So the program counter would tell the processor where in the instruction memory should I fetch the instruction from. And then after I finish an instruction, which is the next clock cycle or a few clock cycles later, I would fetch another instructions for execution, right? And how many of this would tell you how much time to execute, would affect how much time to execute this, and how long does it take to execute each of this will give you the total execution time. So that's why we come up with this equation, because how many of this is actually instructions per program, and how long does it take to execute a program is actually cycles per instruction, seconds per cycle. Right? That's how we derive that performance equation. So if you look at the question, right, the answer that I was expecting is that first of all, tell me execution time like this, and then you can directly relate each of this to this, and then finally got the answer, right? 5 seconds. All right. So hopefully that will give us a pretty good start of the quarter. And now let's look at the second question. Let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so, well, it doesn't show up, but since this is the first time, the first lecture we start practicing theory instruction, so why don't you talk to your friends for another maybe 2 minutes, and let me know the answer after you're done with your discussion. Go.
So I think that's correct. The number has to 13 times the max an hour away. Yeah, 8. And the max.
This percentage is
Yeah. Why?
Yeah.
And why that's good.
Yeah.
Oh yeah. That's good.
I'm saying like why is it why are we doing CPI?
Yes.
Maybe that. Midpoint. I put a midpoint. Because I'm looking for some water.
So if there's
Yeah. And so that part. Yeah, so that part on the good side. We just use
I felt like
this part. And but this day it's just 20% off the top 10 days. So that means this is
All right, let's wrap up in 15 seconds.
delivery not. Like this bag of enough.
All right, 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, 24 of you believe well, 25 of you believe the answer is D. All right, so now I would like to ask some of you to tell us what's your thoughts about how you find your like, tell us like how you got your answer. Okay, what's your name? Okay, so find out the answer.
Why do you? I think it's
So how do I define a VR? Okay, so something like that. So here we go. All right, so the VR is defined by extrusion times X. The extrusion time is exactly the same as the tension. What's the information? Equation will be instruction problem into cycle for instruction. Here and A Y A 14 A All right. So in terms of the answer as well. You guys know it's 5/4, so that's how we get the answer as C, right? So, so first of all, right, it's really important that we have a consensus of how to calculate the speed up. So why this book is called Computer Architecture, a Quantitative Approach. So the textbook is called Quantitative Approach is because before this book, everyone is trying to say, my computer is the best, and my computer is 1 time better than yours, right? And there is no formal definition about how to calculate by what quantity is better. So that's why this book is important, is essential in computer architecture, is because, well, although this is kind of like a very basic formula from today, but you know, like in the very beginning, if nobody say that this is how we should calculate the speed up, everyone would use their own metrics, right? So in computer architecture, when we talk about speed up, it's the relative performance between 2 machines, and say these 2 machines X and Y. We say Y is n times faster than X. This n must be calculated by execution time X and execution time Y. That's the only definition of speed up in computer architecture. The only definition. So when we talk about speed up, it always refers to this. If you are missing, like if you don't tell people what's your X, then we have no idea if that's the right way of comparing with each other. Right? So this is really important because with a unified definition of speed up, we can finally compare fairly from one machine to another. So that's the only definition. All right. So so the speed up of Y over X is, when we say Y over X, is always execution time X over execution time. And this is really important, right? Because without that, there is no fair comparison. It's always like a lot of us were growing up in Asia, and like lots of like your parents must always say that my son, my daughter, my kids are the best, right? Like he went to the best school in the United States, right? Like Harvard, which I don't agree, right? Or like Berkeley, I don't agree, right? UCLA, I don't agree. Maybe UC Riverside is better than Harvard in some sense. We'll definitely find out something, right? Like yeah, like we are ranked #1 in social mobility, right? So I can always find a ranking saying that my kids are attending the best school, right? There is no standard. So you need to find out, okay, everybody is compared on the basis of like US News, or everyone should compare it to social mobility. And I do think social mobility is important in a way that it tells that, well, no matter who you are, we can make you success, right? But I don't think Harvard has that kind of ability because well, it's broken. Oh, you know, like some famous school, right? They got the best student in the very beginning, so it's easy to project their success. But you know, like UCR is doing a good job in a way that a lot of us are not coming from the best like background, but we can still success, right? So in our ranking, we are the best. So I can always say that. Well, if your parents can always say that my kid is going to the best school in the United States, right? So you really so this is like an example that why you need a standard way of comparing one against another, right? So that's the definition of speed. That's the only definition of speed up in computer architecture. So if you look over the speed up for this question, right, and you want to formalize it, you have to get the execution time Y as what you guys just described, and then with that you can finally say, well, the speed up is 1.20. All right. So now the next part: what affects each factor in performance equation? We already know that for performance equation we have instruction count, we have CPI, we have cycle time. So now I'm asking you, as a programmer, A lot of us are. How can we affect performance? Yes.
Do you mean as a programmer writing on any written computer or somebody designing?
Like you can write any code to affect that. As a coder, as a programmer, you can. Anything programmer can do.
Oh, yeah.
All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so again, it doesn't work out. I will figure out how to make it work out next time. But apparently, I can tell you for this question, there's no answer dominating your answer. So why don't you? This is really a question we need peer instruction. So why don't you go ahead, discuss with your friends now.
Yes.
That's why I said. Yeah.
Oh, sorry. This is. Yeah, not about pay.
All right, let's wrap up in 15 seconds.
Oh yeah.
All right, 5, 4, 3, 2, 1. Time is up. Okay. So after discussion, if you can see my screen, it's still like this, right? So, all right, now still no consensus. So that's why you guys need me. Okay. So can some of you share your thoughts with me? Like, what do you think? What's your name again?
Andrew,
Andrew. Okay. What do you think?
I think it's just one because the other two have to do with hardware.
Okay. So what are the one that you think you can directly impact?
The one you can directly impact is the instructions per program.
Okay.
The,
Instruction count.
yeah, instruction count.
And how can you affect it?
You can affect that by changing your program to the point where it has less.
Like implementing different algorithms.
Yeah, different algorithms, so you have to use less load, store, and code for the program to be more efficient.
Okay, other thoughts? Other?
Also, if I have a better compiler that could type of program.
Okay, so is compiler,
We could program the compiler.
you can program compiler, right? But as a programmer, can you, well, yeah, but that's actually a compiler's job, from your job. You can change your compiler, but that's a compiler, but you don't change the program, and you don't. So, okay, by programmer, I think that you can change your program in different ways to, and assuming other things are. Then, what do you guys think? If the only factor, you have the machine, the only factor you can change. Well, I can change the program.
But you could also overclock the CPU though.
You can also but here's the thing, right? If you are
So change some settings in the
you can start setting it down, what if the machine is remote? Well, think about this, right? Like, you will figure out that, well, the programmer can do a lot of things, right? So let's go. Okay, before we go to the answer I have in mind, let's go through this problem first, and that's like, what do you guys think about this? Let me know what you guys think about this. Yeah, this is another question. Yes. Is it going on?
Yeah.
Okay.
Did you remember he asked the same question? It was almost like there was one slide where everything else was there.
All right, individual thinking, individual thinking. This one, this one.
So if it's B, then it needs to stay one year and then take another.
All right, wrap up in 15 seconds.
Or that's the next sense.
5, 4, 3, 2, 1. Time is up. lot. All right. So why? Well, so for this question, we do see some variance in the answer. So why don't you go ahead and discuss with your friends? Yeah. Dude, I love thinking about
So they get where they're only 60 days. I mean, especially on five
Let's say like that, that's what AI did. Because Jason.
No, that's
Five, four, three, two, one, one. Self-made. All right. So after discussion, 31 of you think it's one, but you know sometimes in salt there is one, right? But that one may be different one from another. So let me ask some of you to share with me what's the one you have in mind.
cost per instruction, cycles per instruction.
Cycles per instruction, how about you? Yeah. Cycles per instruction, other answers. Okay, so what this example tells you. So what was the previous question about?
Yeah, can be affected by.
Right, so previous question we were asking how many can a program affect? Most of you agree that, well, instruction count, right? I can do it, right? Doesn't this question tell you that I can affect this as well? Right? But how did you get that? Or you, right? Because I think I have tortured you enough. Right, so I will give you a release. You're free.
The iCache will assign the different speed between the two codes because we know the IC is the same in A and B, but
How do you know that the instruction count is wrong?
because the
The loop structure is about the same.
Yes.
And from the algorithm wise, are they different?
algorithm is the same because
They are the same class.
it's a array size square. Yes, it is.
And it's the same processor, so how about the clock?
Yes, the clock rate is the same as
All right. So for this one, right? First of all, which side is faster, left hand or right? Left side. You guys think left side will be faster, but do you guys know how much faster it's going to be?
Oh, like a lot faster.
Yeah, but okay. So according to our definition about performance, right? How many times faster the left hand side over the right hand side? How many?
Twice as fast.
Twice? Okay. How? What else? 10 times. Okay, let's see. Right. So I have a program here, and if you look at the code, it's exactly the same as I show you. And I have two versions of this. And oh wow. So here it says if I define version A, it will run this pieces of code. Else, it will run this pieces of code, right? So if version A, it goes to it's iterating on I first and then J, and the other way flip around, right? And here is a sanity check. Make sure that both of them will generate the same result. And okay, let me make the program, make clean, and make the program. So you know that, well, like, okay, with this one, right? Okay, so now, let me try this, right? Time it. So this is the version A. Okay, it takes about 3 seconds, right? And now for version B, it takes about 6 seconds. So some of you say about twice faster. That's actually a pretty good estimation, right? So this is an example tells you that you should drop the algorithm class because they tell you that you should always evaluating the performance of a program based on complexity, but both left-hand side and right-hand side have the same complexity. And if you learn assembly language, you know that, well, they should have roughly about the same instruction count. However, and it's the same processor, so the processor clock rate is not going to be changing a lot. And now, finally, right, so what really makes the performance different is the CPI, right? So that's the only thing that's different according to these 3 factors, right? So that's, and we can use, if you know, if you want to figure out like, okay, how many instructions or how fast the cycle time we can use, we have in a program. Actually, there are some performance counters that are available in your processor. And if you are running a Linux system, you can use a program called perf to help you figure that out. And on a Mac, like what I have right now, I have we can use the time profiler, which if you install Xcode, they will come with. And for Intel, they have Intel vTune, but you know Intel is a good friend of Microsoft, so their software is only working on Windows system with Intel processors. So and it needs money. It costs you money, right? So most of the time, well, I'm a poor professor, so I cannot do that, right? So what I'm going to show you today is actually using perf. So perf, what I can show you is that let me see. Sudo perf, and there are a lot of instructions in perf that you can use perf help to figure out, and like this tells you like how to use perf. But today I'm just using the stat, try to gather performance counter statistics. So if I run MADDA, right, it will tell you, okay, so this is the number of instructions, and this is the cycles, and here would give you, okay, instructions per cycle, so it's a flip of CPI, right? So on average, it's 2.32. And for MADDB, number of instructions, right, is about the same, right? Also 14 million. But however, if you look at the instructions per cycle, right, 2.3 versus 1.17, right? So that's really something makes the difference, right? So here it tells you that, well, even though both programs, they have exactly the same complexity in the algorithm or exactly the same instruction count depending on how programmer uses this, how programmer implement this algorithm will significantly change performance. And this example is a very simple example that just switch the loop index. Still gives you the same result. However, performance is twice different. So this one tells you that, well, programmer can make CPI better or worse. All right. So now for this one, right, the one thing that affects the factor is actually the CPI. Okay, so a lot of you saw this before in the first lecture, and some of you do have questions on this. So based on the knowledge that you learned, can you answer the question like what programmer changes in this pieces of code to make the performance better? All right, in 15 seconds. Five, four, three, two, one. Time is up. Okay, so for this question, I see a bipolar distribution of the answer. So it's actually a reason why we need discussion. So go ahead, 90 seconds.
Oh yeah, yeah. Wait. Yeah, I
Yeah, the questions like that. I was a little off. Oh, it's still not given, I want to- All right, 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, most of you think the answer is D. So, why?
Wait, what's the answer?
I don't know the answer yet, but looks like most of you think it's D now. Okay, you want to explain why?
Sure. I think my choice is D, IC, and CPI because first the source is added.
Right.
So there are more code. So the instructions becomes the instruction becomes larger, and
So execution time equal to
it is equal to IC by CPI.
okay. So you make the instruction larger.
Larger, but the CPI becomes lower.
So now the question is that we want to better. So making the instruction count larger, is it contributing to directly contributing to better?
So that's also what we talked about. That's a kind of, I think that's an interpretation problem. Because I think the programmer changes both factors, but the CPI becomes better optimization. So it's overweight the negative feedback form.
Right. So you got one thing, right? So we actually made the instruction count this factor worse.
Yeah.
Right. So from better performance part is actually from the CPI. Right. So I would say if I were you, I would think the answer is only A because we are actually making B worse. All right. So some of you were saying about like cycle time, right? So in fact, as a programmer, you can use APIs to change the cycle time. So now, there's a document released by Intel and software.intel.com, right? It tells you that what kind of CPI you can use to change the cycle time. But now I just want to show you that, well, through a little script which you can call through your code to change the cycle time of your processor. So here I have just this one line of code, and this one line of code, I can input a number to change this the desired cycle time at any moment. So like, okay, so right now, well, this is a really huge processor. So right now, if you look at that, my processor is running at 1.2 gigahertz. And what I could do is that I can use this script change. Okay, let me see. 1.8. Is that the right number? No, that's too much. Right?
Wait, does it give you like a range for safety, or did you like set it?
Yeah.
And then never
Well, so there are some value. If you try to set it, your computer will reject.
Oh, okay.
Yeah. So don't worry about that. The computer is so smart. Wait. How do I do this? Okay. SH change frequency and 1.8. Is this the right number? Permission denied. Cannot. Hey, it works yesterday.
Only 5 0. Oh, you know.
Yeah. Okay. Okay, let me do this. Let me just copy this line.
Hey, that.
Let's see.
Yeah, for gigahertz. I think he's doing megahertz right now.
I am doing let's see what it says first, okay? Is it there? Okay, here we go. Right, so that's the the minimum frequency for now. So what I can do is okay, shoot. All right, cool down, man. Don't be nervous. All right, I will do it. Wait, what happened? Oh. Okay, let me echo this number. Like 1A, 0. Okay, here we go. Finally, right? And then now let me show the processor speed. Right? See? It used to be It used to be 1.2 gigahertz, right? But now it goes to 1.8 gigahertz here, right? Just because.
That says megahertz?
Yeah, megahertz, yeah.
But it says gigahertz 2 lines up.
Well, so this is, okay, so that's interesting, right? So this is the model of the processor, right? Saying that it can run at 1.8, right? But actually you can set the frequency to be 1.1, right? So now if I change the number again, right? And then you will immediately see the processor speed drops, right? So now, if you look at a demo, right, how powerful you guys are, right? You can affect instruction count directly through the algorithm. You can also affect the instruction count, and through API, through instructions exposed by your processor, you can affect everything. You are the most powerful part of the computer system. So that's why we want to teach you computer architecture. All right. So the answer is actually the programmer can affect everything. Okay. So we are running out of time today, and I hope you learned one thing, that you are the most powerful over the world of computer. And before you leave the classroom, there are several things that I want to let you know. So first of all, we have another reading quiz due next Monday before the lecture. And again, don't be panicked. We'll drop your least, the least performing reading quizzes, and you have 2 shots, both unlimited time. And if you still don't know where to get the slides, where to do the reading quizzes, where to discuss, website, eLearn, and Piazza. And if you want to remind yourself what you have learned from the class, or if you cannot attend any lecture, we do have everything recorded online. And I put it on YouTube, so it's very easy to access. You don't need the 2-factor authentication. Other than that, enjoy the rest of the week. I will see you next Monday.
You said that the slides were from last year?
Yeah.
Hey, I'm confused though, because I pulled it from the website, like right here. That was the exact slide that I got. This one, right?
Maybe a link.
2021 for a fall semester.
Okay, then I probably. Okay, so the recap slide you see this today, right?
Yeah, that's the one that I got.
Okay, so here's the thing. This is the slide for all the performance sections, and we have 3 lectures on.
Okay.
Yeah.
Oh.
So this is like something you will see later. So yeah, those are their purpose.
But I was confused because like the slide that you're pointing to.
Yeah, because we are going there. We are going there next lecture. Yep.
A couple questions from the reading. 'Cause, I remember in the reading section you talked about instead of instruction, the architects might consider to like optimize just for that. I'm just wondering like how the architect would do that kind of mathematics. determine like what to actually be
So you were saying how
how do they choose which part of the like group of instruction they want to.
so that will be the next lecture.
Oh.
But typically we will. So the short answer is that there are things like
I know
profiler.
they're like going for like the common case, but
Right.
like
Yeah, but
specifically-
so next lecture I will talk about it. But
Okay.
today, like we talk about big tune,
Okay.
Intel big tune. The reason why they're selling you that for money because they would give you like, okay, which phase of the program takes the most amount of time and which part of it is slow, so you can address those issues.
Okay.
Right. So basically, the short answer is that profiling tool. They tell you which function takes the most of the time and how you address it. Yep.
Thank you.
Will you explain about the quizzes in the class?
You mean the quizzes?
Yes.
E-learn.
No, I mean, I got a little confused about the answers. So, will you explain that in the class? Or I can
So
answer
if
through
you,
the
yeah,
PI?
you probably have to go ask through Piazza or you have to ask through Office. Yeah, but what was the question?
It's about the, I don't know the question. The third one is about the CPA, IC, and the IC hardware effect.
Okay, so yeah, so
the answer is CT, right?
yeah, I don't quite remember exactly the provenance, but it would be nice like if you go back and review, and if you still have questions, let me know. Yep.
I have a question about the two codes that access the matrix.
Mhm.
So the difference between the two is CPI, right?
Is the CPI? Yeah.
Exactly, but I'm not quite sure about why does they have difference in CPI.
Okay, so the answer is that because the access pattern to memory is different, and because of that, so and processor itself has some kind of optimization if you access sequentially in a row order. But if you do it in a column order, like the right hand side doing, it's not in favor of the processors.
Okay.
Yeah.
So the instruction will take more time to like.
Each
fetch
instruction would
something.
take time, more time to fetch those things. And without knowing that your processor is doing this kind of stuff in the backend, there's no way that you know this is the bad.
Okay.
All right.
Thank you.
Professor, if there are more load and store, there won't be more load and store if we go column by.
No, I think the same amount of load store. You see the instruction count is about the same. It's just because the way you navigate your data in this way, it will be slower. But why is it slower? The memory hierarchy part will answer that. But the reason is because there's something called cache in the processor. And, yeah, yeah. But the same amount of load store instructions.
Do you mind if I pretend but I don't roll this?
Sure. I mean, there's no way I can prevent you from from sitting here, right? Yeah.
Second quiz, and I mean compare the speed of x and y.
Uh-huh.
You said that how much faster, right, on the question.
Let me figure out how to close this first.